and share my screen. So can you see my screen? Yes, no, please.
Yes, sir, it is visible.
Okay. So we were talking about routing. Remember, we are talking about a network now where every node is not, the nodes are basically my routers, and there are some nodes which are end devices which produce and consume data. And this data is being carried through a network of routers. And every router cannot be directly connected to everyone else. So it's a graph basically. It's an arbitrary graph. And then in this arbitrary graph, remember, we are talking about packet switched datagrams, which means your data is broken up into some maximum sized packets. A header is put on every packet, and then these packets are sent independently into this network. Okay? And the router will look at each packet. It's a datagram approach. So the router will look at each packet independently, and based on the header information, we'll look at the exact header information for IP and all later on. We'll decide which way to send this thing. Okay. But then to decide which way to send this in, and this is something for virtual circuits, everything, you need to give a source and a destination. The source wants to send a packet to a destination. Somebody will have to find the route. Okay, because say, oh, you have to follow this router, then that router, then this router, then this router, and so on. So just finding a path in the graph. Now you all know how to find a path between two nodes in the graph. Okay, but the problem here is that the network may not be fully available to everybody. Okay, so should I always rely on collecting the entire network information centrally at some node and then compute the path? Or should I do something else? Okay, so we'll see what approaches are done to find this routing path. And we ended the class, last class, by saying that what will happen is basically every node will keep a routing table. Okay, it will have some entries. We'll just shortly look at what entries, but the first field is going to be every node that is reachable from this node. So it's one node for every destination that is reachable. Okay, so when a packet comes, somewhere in the header, there will be a field which says what is the final destination of that packet. And then I will look at the appropriate table entry, try to find it. I may have it, I may not have it, I should have it, but sometimes we'll see temporarily I may not have it. And if I find an entry, I take that appropriate decision. So what does that entry has? Okay. So what is the route? So this table that I talked about, okay, what are the fields out here, right? So I said the first field will be destination. Okay, some idea of the final node. For IP, it will be some IP address or something. Okay. Then there will be a field called next hop. Okay. So all routing tables will have these fields and some more basically. So next hop basically says, now I do not know, I don't want to store the entire path to the destination. Okay. But I want to store, to reach that destination, out of the nodes that this router is directly connected to, what is the next node that should forward the packet? Okay. So if I have a network like this, so this router's routing table, if I look at, okay, so now finally my destination may be somewhere here. Okay, but if it has 4 neighbors ABCD, for this destination, we'll give a field saying destination, and so A to say that to reach that destination, there may be other routers it doesn't know of, but the next node that I send it to is, that's all it needs to know, because when it reaches A will do the same thing. A has now got a packet for the destination. A will look up its routing table, and if the route is set up properly, it will decide, oh, the next node that I should send is some F. Okay, out of all the nodes that goes out of this space. All right. So this packet, so every routing table will kind of forward it to the next hop, and the next hop will apply the same logic to forward to the next hop, and so on, until it reaches a node where the node checks and says the destination, so it does not forward it. And then there will be something called the cost, which is the cost of this route. Now, what is the cost? Definition of cost can vary depending on the routing protocols, features, and so on. One common metric is the number of hops. What is the number of links I have to traverse to the destination? Okay. So typically, this will have a thing like, so I'll have a destination, so I will have an entry like X, A, 12, let's say, okay, which basically says there is a route from me, whatever this routing table whose router is, to the final destination X. I don't know where it is, okay, but I know it's 12 hops away from me, okay, and the next node out of all the nodes that I am directly connected to towards that destination is A. So when a packet comes, I will look up the destination field. If it is X, I look up this table to find this entry for X, okay, I will blindly forward it to the next route. A will now do the same thing, and if the route is set up properly, eventually it will reach the destination X. Okay. The cost again can be many other things. Basically, we look at that. There are usually some other fields. We'll skip that for the time being. Not important for us to learn basics of routing protocol. When we do IP, I'll show you examples of actual IP routing tables on your machines as well. These are two terms that you will see, and I want you to understand the difference between them. Okay, even though sometimes we use the term routing for both. Routing deals with the process of finding the route, so that building this routing table. So there will be protocols that we'll study, okay, which are routing protocols whose job is to run in the background and kind of fill up these table entries at the different nodes. Okay. There are also on-demand routing protocols in other types of networks, which finds the route only when a packet has to be sent to the destination. It does not find it after. Okay, but we will not do this in this course. They are not, internet does not use them. Only very special cases. So this is what we are going to do. So they can run even if no packets need to be sent. It kind of keeps the table ready so that when a packet comes, I know what to do with it immediately. Whereas forwarding is the second step. That when a packet comes, you forward it basically. Okay, so it's done only when a packet arrives at the node whose final destination is not this node. So then you look up this routing table that is built by your routing protocol, and you decide what to do. So this is done in real time. Packet comes, you decide to look at it. So it is forwarding the packet. Whereas routing is building the routing table, which the forwarding entry, which will have the entry which the forwarding process will use. Okay. So you will sometimes loosely route a packet, which is fine. But if somebody asks you basically what is routing and what is forwarding, this is what the difference between the two is. All right. What we will do is basically the routing protocol, not forwarding right now, because we'll see forwarding is simple. Forwarding, you will look up the destination field. We'll see some aspects of it when we do IP. And then if you find an entry, you will just use the next hop field to send it to the next hop. Okay. So forwarding is not complicated. It's finding the matching thing is a little bit, it has some algorithmic aspect to it, we'll discuss, but it's not a complicated process to understand. Routing is, on the other hand, not complicated, but it's how do you fill up these routing tables is important. So what do you want to do? What should be the goals of a routing protocol if you design one? Sorry. First of all, it should be correct. So if I give you a graph and the graph does not change, and I start a routing protocol on it, and this builds these routing tables on all these nodes, eventually they should be correct. Okay? That means if I give a packet to any node, it follows that next hop, next hop, next hop, and all the nodes. It should eventually reach the destination that it's supposed to be. And that should be true for every source destination. So this should happen. Now, temporarily, we'll see it may be incorrect because once a link, for example, if a link breaks, one of your edges in the graph disappears, then the path may change, your route may change that exists in the routing table. It may take some time for everybody to know about the path. Okay? If a path from, let's say, some link in France breaks basically, and it's on my path to my packet to reach US, there'll be some time before that information percolates back to a BSNL router or whatever. So during that time, this route is not correct because the packets will get dropped if I forward along. But that's okay. If I have a stable network where nothing is changing, your routing protocol should eventually find the correct path. It should find the optimal path, ideal. Just compute whatever is best. For example, with respect to the number of links, if we say that I am trying to find the least hop path, the shortest path, okay, in terms of the number of edges it goes to, then the path that the routing protocol finds should be the shortest path. Now, how will it find? Just try to visualize a network. Okay, we'll see, so nobody knows the entire network. To find a path, eventually some messages has to be sent between these nodes. Okay. And these nodes will send some messages to say, oh, I can reach destination. So it's like this. One simple thing is that you can reach X. So you tell everybody around you that I can reach X. Now that's not everybody in the universe. But then those people who heard you can now tell everybody they know that he can reach X. Or rather, they can say I can reach X. Because everybody doesn't need to know how you can reach X basically. So it's a very simple protocol, but you can percolate this information like this. Okay, but then there are messages that are being sent. Okay. Now remember that final goal of having a network is to send the data, the actual data that you want to send. Everything else you are doing so that the data actually goes. So everything else is an overhead. Okay. So you want the routing protocol to send as few messages as possible in order to establish the route. Because the same routers are going to handle your router packets also, routing protocol packets also. Which means that they can handle some part of their capacity is utilized to handle these routing protocol packets and therefore not having the data protocol packets. Okay. So it should be low overhead, should not send too many messages. It should be robust, which basically, as I said, that if there is a link failure, node failure, which keeps on happening in the net, okay, route should be automatically updated. Or even if there is no failure, if you are using a metric like traffic load, so you are trying to find the least loaded path. The load is something that will dynamically change. So if it changes and some path become now least loaded, your routing protocol should automatically find that path and update everybody's route. You should not have to do anything manually and watch the network and so on. That's not possible. And not only should it be robust, you should do it fast. Okay. That when you update this automatically update, it should be rapid. So what is the time since, for example, from the time that a link goes down till everybody's routing table gets updated, and again proper with respect to the new graph. Okay. So remember these things, understand their importance. So whenever you take a routing protocol, you say, is it correct? Is it finding the best route depending on how I define best? How many messages is transmitting? Can it handle change in topology, change in weights of the edges and so on? Okay. And how fast does it handle that change? Basically. So these are the 5 things on which we evaluated routing protocol. Is it okay? Yes, no? Can you hear me? Yes, no, please.
Yes, sir.
Oh, good.
Yes, sir.
Thank you. Okay. So this is not really this performance metric, but this is more this cost metric that I talked about. Some examples. So this I already talked about. Minimum number of hops. Okay. You can say minimum delay, total delay. Okay. Maximum throughput. Maximum or minimum traffic load. Okay. Now you see this thing is more static. This will change. Links go down, nodes go down, etc., etc. But these things will probably change more often than this one. It's something just a point to note. Okay, because see, for example, what the delay on a link will depend on how congested the link is. The link will propagate things. That's just the link propagation delay. But the routers at the two ends, if there are a lot of packets being sent, this router will take a little bit more time to process things. So if I have a path like this, and I'm from the source and the destination, and I'm trying to find the least delay path. Now, how congested this router is will depend on who else is sending packets to this that goes to this router. Okay. Now, sometimes there will be a lot of packets, so this delay will go up for this source to destination. Sometimes there will be less packets, so this delay will go down. Okay. And internet traffic is, or network traffic is normally burst. Okay. You send something for some time, you transfer a file. Okay. For some time, you're transferring the file, then you do nothing for a little bit. Okay. So these things, delay, okay, traffic carried, etc. These are more dynamic, whereas number of hops, types of links, available bandwidth, okay, these are more static things. When you design the link, you know that this link is optical fiber and has bandwidth of this much. Okay. So bandwidth will depend how the data rate will depend also on the equipment that you put on the other side. So you can put an optical fiber, but you put only 1 Gbps routers on this side. Okay. So even if this fiber can carry a lot of things, its traffic is actually limited to 1 Gbps. Actually, practically, if you have 1 Gbps, it's around 50, 60, 70% of it maximum. But you can still, the link is there. So if you put a 10 Gbps router, you can utilize more capacity. So you can define what should be the cost. It's like the weight on the link, weight on the graph, the edges of the graph basically. So finally, what you are trying to do is just finding kind of shortest paths on a weighted graph. So only thing, your graph may keep on changing in terms of topology, in terms of weights, basically. And your protocol has to be able to handle that. Next thing is when and where is the routing decision taken. Okay. When is, okay. So this is what we are going to do. In data graph, that is per packet. So every time, okay. Actually, this is, I told you the routing and forwarding, okay. But this is not, this slide I will modify, okay. So this is not exactly when is not per packet or something. Okay, so per packet is only forwarding, not the routing basically. Okay. So who decides the route? This slide is a little bit confusing. I'm sorry. Okay. So, but the thing is where is this? So who makes these algorithms run? Okay. Is it that there is one node that collects all the information from everybody and does it? And then percolates, kind of sends the routing tables to everybody. That this is your routing table, this is your routing table, this is your routing table, and so on, knowing the topology. Now that would be simple in terms of algorithms because you know how to do that. You can do like all pair shortest path and so on. Okay. But then somebody has to collect all that information just to know the complete network. Okay. It has to monitor for the changes and so on and so forth. Okay. So that is simply usually not done. What we do is you do distributed. So centralized will work. So what I just described earlier is centralized, one central node. Okay. So one node decides the routing tables for everyone. Okay. But then that understand that can only be done for small networks with not too much changes occurring. So, okay. Or this is what we'll study. So we'll see every node will do something. Okay. Every node will run some algorithm, exchange some messages with its neighbors. Okay. But then eventually, if you look at the network from outside, just think that you're an observer. Okay. You will see the routing tables getting formed in each of the nodes automatically. So they will exchange packets for some time. And if the network does not change, eventually you will see every node's routing table will be correct and optimal and all, depending on the cost base. So there is no central node which has the responsibility of computing the routing tables for everybody. Everybody computes their own routing table by running a protocol that exchanges messages with their neighbors. How that happens, we'll see. So this is what is being done at the all the network routing protocols that you study will be distributed. But there is one more possibility. Okay, it's called source routing. Okay? So this slide I will modify. Okay, this slide I will modify because routing and forwarding is kind of mixed up in this slide. Okay, but anyway, since we are talking about this, so source routing is more for the forwarding thing. Okay, so but let me mention it anyway since we have done it. So normally, as I said, when a router gets a packet, it looks at the destination field, looks at its routing table, and then decides what's the next stop to go to. Okay. Whereas with source routing, the source will put the entire path inside the packet. So it does not have to look up any routing table or anything. Okay. So it's more a forwarding thing. How the source will know the route and all, don't worry about it. That's a separate question. That's the routing question. But forwarding wise is instead of just the destination field, all the intermediate level routers that it should pass through are actually specified in the source, in the packet itself. So all the router has to do is to see that it is in the path, the node is correct, the packet has come correctly to it, take out that and send it to the next router on the path, basically. But again, I will modify this slide because this is more a forwarding thing, this is more a forwarding thing, these two are the routing thing, basically. All right, so we know the goals of routing protocols. We know what the routing table should look like. What is it that I'm trying to build? How to use them and everything. Now look at the routing protocols actually. So what are the kind of broad strategies? The simplest is fixed and static. So you do manual. Okay. So manually you can enter some routes, and we do sometimes enter some routes manually because they don't change. We always want it to happen in certain environments. Okay, so nothing to be learned. We say this should not change. But usually, very small routes in a larger network, or this works only for very small networks. Okay. For example, your desktop, okay, your laptop desktop does not run a routing protocol. It will have a routing table. I'll show you the IP routing table there. But it does not run a routing protocol. Okay. So those are configured manually. Manually meaning when your system boots up, there are some default things for the network configuration which writes the program that writes in. But that's not a routing protocol. It's as if that you have entered in manually. It's just the program has all those things written in. Okay. But it does not converse with any other machine to know, exchange routing protocol messages and so on. So it's manual. Random, let's do this. Basically, random routing is again, it says, I don't really build a routing table. Okay. But when a packet comes, basically, this routing table does not really exist. Okay. When a packet comes, I'll just randomly choose one of the numbers. So that's you can understand, there are, if you're interested, you can look at something called random walks. Okay. And random walks are very nice things. So basically, if you have a graph, okay, and you think that you start walking from one node. Now, from that one node, you have edges going out to multiple nodes. So you choose an edge randomly, okay, uniformly at random from all the options that are available. And you keep on doing that every night. So you kind of randomly walking the graph. Okay. So it has very, very interesting properties as to eventually you will cover the graph with high probability. Okay, within what time? Okay. So that there are very nice properties, very nice applications. Okay, but mostly many theoretical things. So this is something that is not good for routing. Okay. Flooding is the other approach. It's kind of a one end of routing thing, which says that don't build the routing table because you have no clue who is where. Okay, don't try to learn it. So you have no routing table. So this is also forwarding, but this you want to talk about routing strategy because it's a strategy which says don't build the routing table. Okay, but send a packet to all neighbors. Okay. So we will come to that. An adaptive dynamic is the one that we are going to really do, which basically says that you take, you build the routing table when nodes, links change, you rebuild the routing table, okay, you exchange messages. So the proper routing protocol runs. So fixed static, no routing protocol, the routing table is built manually. Flooding, also no routing table at all, but packets are sent flooded. We'll see what that means. Random, again, no routing table, just choose one randomly. Okay. Adaptive is the one that actually builds the routing table, automatically adapts to changes and so on. Okay. So this you will in practice see for small networks or for some routes in large networks. This is what all internet routing protocols are based on. Okay. But flooding is kind of an initial strategy for many things. So fixed static, as I said already, so already discussed this thing, so you can leave this. Okay. It's all manual. You have to, it's not adapt to changes or something. Flooding is, as I said, okay. No network info, packet sent to node by every node. Okay. So if I have a graph, okay, what will happen is if this will send a packet to this. This will receive send this packet here. This will receive send this packet here. This will receive send this packet here. Sorry, here and here. This will send here and here. And even if the graph has something else, the same thing will happen. So you can see eventually the destination will get it. Okay. So incoming packets are transmitted on every link except the incoming link. So eventually a number of copies will arrive at destination. If you have a destination, you will get one copy from each incoming link eventually. And you can, usually it's called controlled flooding. Usually flooding normally means controlled flooding, that you can put a number, sequence number or something with the packet. So look at this node. When it gets from here, it transmitted already here and here. So when it gets again from here, it should not transmit again. Okay. That is redundant because it's already sent here, already sent here. So it can just keep a track of the sequence number of the packets it has already transmitted. Therefore, if it receives again, it can check that table to see it's a duplicate and not transmitted. Okay. So the advantage is that you will eventually get the packet. It kind of explores all possible paths. Okay. What is the disadvantage? So it is correct, of course. It's optimal. Okay. What is the disadvantage? Come on, be simple. There is just too many messages. Okay, so just to send one packet, on every link there will be a message coming on this side and a message coming on this side. So over one packet you will send 2 messages, which is just too much. And think of that your source is here, the destination is somewhere here, and here is a network which has no link to the destination. The packet will still go and reach everybody in the destination. So flooding is not used for routing. But flooding has, you will see many protocols, okay? Very interesting aspect that when you don't know anything about the network, it's a good way of discovering something of the network. So we'll see the initial stages of many things, okay? Sometimes, okay? Where you flood the information to let everybody know something. Based on that information, they build up something so that the later things can be improved. Okay? Let me tell you a little bit of graph theory. Okay? So you see, think of a network. Okay. Now, if you want to consider this node, if you want to broadcast a message to everybody, that means you should send everybody some message. Okay. Forget network, it's plain simple algorithms. What is the best way to send a message to everybody? With the least number of messages sent, but it should reach everybody. Anyone? what algorithmic structure would you follow would help you if you want to send a message from here. You don't see it here, but what would be the structure that would be good for you if you send a message here and you want to ensure that every node gets that message, but with the least possible number of messages being sent over the network. Anyone? What graph structure does that remind you of?
Is it a tree, sir? A minimum?
Yes, it's a spanning tree. Exactly. If I had a spanning tree, okay, just suppose I had a spanning tree like this. Okay, so you had n minus 1 edges. I'll just do this. I'll send the message to only my neighbors. They will forward to their children and so on and so forth. Okay, this is the root kind of. So you will be able to send the message with only n minus 1 total messages. Everybody will reach. Right? But you don't have the spanning tree. So to build a spanning tree, okay, and I have no clue about the network. And remember, I have to do a distributed thing. Okay, everybody just needs to know who its parent is, who its children is. They don't need to know the rest of the network. If it gets something from the parent, they just pass it to the children. That's how my broadcast is happening. Okay, so I'll do this. Think of a protocol like this. Okay, I have the graph already. Initially, since I don't have the thing, I will flood the message. The first message. Okay, when I flood it, it will guarantee everybody will reach it, but only thing it will get too much cost, too weak cost. And then, but I will do this as a side thing of that first message. So this node will get a message from here, eventually from here and from here. Now try to visualize it. Okay, that this message will come at different times. Okay, it chooses the node from which it gets the message first as its parent in the spanning tree. So there's a parent field here at every node. It says, oh, I've got it from this first. Let me choose this as my whatever A as my parent. And they really inform that node that I'm your child. So every node will get it for the first time from exactly one node. So there'll be exactly one parent. Okay, and you can very easily verify you will end up with a spanning tree. This is one application of flooding. At the beginning, I have no clue about the structure of the network, so I use flooding. But as part of that, I build that structure so that my subsequent broadcasts do not take this 2 time, they only take n minus 1 time of the number of messages. Sorry. Okay, so that's where we will see sometimes flooding being used, because sometimes we don't want to know what the network is, kind of discovering the network information, sort of, basically. Okay. Is it clear? Yes, no?
Yes, sir.
Okay, so this I have already talked about this. All possible writes are tried, very robust. At least one packet will have minimum cost out. Okay, all nodes are visited, but no routes remembered. So too many copies of a packet. So no routing table, nothing. Basically. So you flood every time. Okay, but it's good for discovering things. Actually, it's on-demand routing that I said will not do. Okay, it's only done in something called ad hoc networks and so on. They do that on a packet. They first flood, but then they build the route. Just kind of similar to what I've said. Okay. Random routing we already discussed. And adaptive routing is what we are going to study. It's used by almost all packet switching networks. Internet being one of the the network we're talking about. Everything. It has every possible routing decision, changes, condition, failure, congestion, that increases delay, anything. Okay. It will require the info about the network. Obviously, it's more complex. Okay. And we'll see there's a trade-off between the quality of network info and overhead. Anyway, I think we'll come back to these points. They don't make sense right now. Let's start looking at one of them at least today. So broadly, there are these two major types, distance vector and link state routing. Okay. There is something called path vector. I'll see whether I keep it separately or not. So once we do distance vector, very end of the course, I'll talk a little bit about it. But this is kind of, if you understand distance vector, you understand this basically. And all internet protocols, routing protocols are based on this. So we'll do distance vector today, and link state we'll see whether we do that. Okay, now I want you to focus. This is just for information. It's based on Bellman-Ford shortest path. Okay. I'll have pictures. I'll have, I will draw an example and so on. But understand what is happening. Remember, you have routing table entries. Okay, and we'll focus on only these three fields: P, Q, C. P is the destination, Q is the next stop, C is the cost. So this PQC is telling you that, and this is the node XS routing table. It says that X has a path to the destination P that go through its neighbor node Q, which is the next stop, and the total cost of the path, whatever my definition of cost is C. We've already seen that, so you will have other entries like this for different destinations. Okay. So each node has a routing table like this. Initially, the routing table will be all empty. Okay, we'll work out an example. So each node will periodically send its routing table to all its neighbors, everybody. So what is periodic? Okay, all. Okay. But what it sends is not the PQC. Okay, it sends basically. Oh, fine. Let's keep that thing there. Okay, PQC. Now, how does a node know if a link is broken? It's basically, so each node, so think of X and Y is supposed to receive a routing table from X every so many things, for example, every 30 seconds or so. So if it does not receive it for, let's say, 5 times that, 6 times that or something, it will assume that the link is broken. Because if the link was up, then it would have received the XS routing table. So either the link is broken or the node X is down. But for all practical purposes to Y, it cannot use the XY link. Okay. So that's how you detect a link is broken up. Now Y gets the XS routing table. So what it will do is, it'll update the information. We'll see exactly how on any node P at Y. If the path through Y is lower cost than the path, okay, rather this is the other way around I've talked to, receiving the routing table at X from Y, it sees whether Y is advertising a path to the same node P that is a lower cost than the path that X knows currently. Or here is the other one, you just note it right now. Y is the next stop on the current path to P. We'll talk about this. Okay. So let's look at a little bit more detail. So whatever the definition of cost that we're using, so this is X receiving the routing table of Y. Okay, it's only between neighbors. Routing tables are not propagated directly. Only the neighbors exchange their routing tables. Okay. So what does X do when it gets a routing table? So suppose D is the cost of the link X1. For example, if I'm using just the number of hops, D is equal to 1 because it's one link. If I'm using delay, there is some estimate of that. That's a separate part that has to be supplied to the routing protocol. Okay. So X on receiving the routing table from Y will do this. He'll look at the routing table of Y, each entry PQC. Okay. So there are two possibilities. So this Y is table, okay, that it has received, and this is X's table. So it has an entry PQC. Okay. So there are two possibilities. First of all, X does not know about any path to P. Okay. For whatever reason. If it does not, then it will end P because it's a new destination. It knows how to reach through Y. Y is the next hop. Okay. And what is the cost of this? So from Y to P, its cost is P. Along with that, the link cost is B, sorry, C. Along with that, the link cost is B. So this cost becomes C plus D. Are you with me? Yes, no, please.
Yes, sir.
Okay. Or the other option is there is already an entry, okay, for P. So let the current entry level P sum next of R. So basically it says that P, sorry, X has a neighbor R through which it has a path to P, and the total cost of this path is sub C dashed. Okay. Now Y is telling that it has a path to P of cost C. So if I go through Y, my cost will be C plus D. So I check if C plus D is less than C dashed or not. If C plus D is less than C dashed, I will remove, because now I know of a path, but this is a lower cost path that I know of. So I will remove my current entry from table. I will add that P Y C plus D out there. Are you with me?
Yes, sir.
Okay. So that's my update. And what is this doing? Don't have too much time today, but we still have 5-7 minutes. That will be fine. So what is this doing? This is saying, basically you say you trust the next hop always. Okay. So if you had a path, so X had a path already, so Y equal to R means its current known path is already through Y. Okay. And this to P, and it knew the path to be C dashed. Okay. Now this path can change for different reasons. There may be a link that has gone down, and that information will be propagated when its routing table comes here. So Y would have updated that routing table. Okay. Or it may come to know a new link comes of a shorter path. So if Y has advertised earlier a path, basically C dashed minus C minus D, that was the cost of this path earlier. Okay. And now it advertises path which is either lower or higher. I don't care. Okay. Because I know my current path goes through Y. Y knows about the path to P, the rest of the path to P. If Y is saying that path has increased or decreased or something, I trust Y that. So if Y is equal to R, that means the path that I know of currently already goes through Y. I update whatever Y is saying always. Does that make sense? Yes, no?
Yes, sir.
Okay. So let's look at a very simple, quick example, and we'll start with this again in the next class. So think of a simple line network. Okay. Draw this with some space. Okay. So this is A, B, C, D. So if I look at the routing table of each of them, initially they all have an entry for this, a dummy entry for yourself. Okay. And nothing else, no other entries. Okay. So now in the first exchange, A and B will exchange. So A will send to B, B will send to A. So when, let's say, B's routing table comes to A, okay, so there is only one entry to look at, okay, and this will have a cost of 0 because B can reach itself with no cost. Okay, so A now sees there is no entry for B in my table. Okay, so it will have add B. What is the next hop? Is B itself. Okay, and this thing, just suppose we are using the link count as my case string, so 0 plus 1, that will be 1. Okay. Now, when C's entry comes to B, for the same reason, you will have an entry called C1 here. Okay. Now, in the next iteration, after next 30 seconds, when B sends the entry again, the routing table again, then A will again look at it, will find BB0, I already have BB1. So same thing, I trust the next hop, and anyway, it's not a lower cost, so it doesn't matter. I keep this. but it finds there's a new entry C. So then its table gets updated to C. But what is the next stop? It goes through B, and this is 1 plus one more link, that is 2. Okay. Meanwhile, this had learned D1. Okay. Same thing is happening for the other direction also. So in the next iteration, this will learn DC1. Okay, because we'll get this table, new entry D does not have the destination. Okay, this is D, this is this. Okay, so in the next iteration, this will come here. So you will get a D, B. So sorry, this will be 2 because 1 plus 1, this will become 3. So this is how the routing table get filled up. With me so far? The same thing is happening in the other direction. So this information from here will take actually 3 periods to propagate. 1 period for C to get the information, next period C will send to B, next period B will send to A. Are you with me? Yes, no?
Yes. Yes, sir.
Okay. Now suppose, so this now is what A's table looks like. Okay. Now suppose this link goes down. Okay. So there is an underlying what we call a hello protocol, they exchange messages, neighboring nodes exchange messages always. Or in this case, as I said, so if this link goes down for quite some time, C will not get any routing update from C, D. So eventually C will detect that this link is broken. Maybe for 5 periods, 6 periods, it does not get anything from it. Okay. So then it will update this thing to, it will say D, if I have found this, will say that I cannot reach it, and this will signify by putting an infinity here. Infinity is just think of one large value. We'll see what the value of infinity is. Okay. Now when it comes here, look at what happens here. So when this routing table now comes here, B finds there is already an entry for D. Okay. So 2 plus 1 is already less than infinity. So it's not because this is short. But B finds, okay, that this update, this DD infinity is coming from, and I have a DC2, it is coming from C, which is the same as my next one. So it basically says that something has happened in the other part, the rest of the path from C to D that I do not know about. But C is telling me, because C knows, C has come to know about it. My path goes through C, so I'll trust C anyway. So this will also update this to infinity blindly. Okay. Next iteration, it will come here. So this will also update your DB3 to infinity. Note that I don't delete this thing immediately. It's very, very important. You'll see the problems with this thing. When I detect this link broken, I don't delete this. Because if I delete this thing kind of stays. If this thing stays, I will keep on forwarding packets for D to C, and then C will not find it out in the forwarding thing. He'll just drop it. Everybody has to eventually know that this route has disappeared. So we'll do DB infinity eventually. Now, if there is another node which was here, okay, a longer path, then that information was also coming through to A. But A was so far ignoring that information because this was 3, that would have been 1, 2, 3, 4, 5. Now that it has become infinity, when this router sends it with the 4th thing, he'll update this to D. Let's say whatever call this X, 5. Is this clear? How this is happening?
Yes, sir, it's clear.
So everything kind of takes some time to propagate. Okay. What's the maximum time it will take to propagate? How many periods? What is the maximum distance 2 nodes can be apart in a graph? Come on. And I have taught you algorithms too also last time. It's more algorithms, one question. So this is the number of periods it will take, the diameter of the graph. The longest, shortest path. Right? Okay, we're out of time. Okay, but I hope you understood the concept of distance vector protocols. So please try to listen to the lecture, kind of think about it before the next class, makes our job easier. So next class we'll start from here and start with an example again, and then look at properties of it, problems with it, what do we do to solve it, and so on. Okay. So basic distance vector is understood, right?
Yes, sir.
Yeah. Okay, we're out of time. So if you have any questions, you can ask.